Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into something both vast and strangely close, a hidden hollowness surrounding everything we know. We'll drift gently into what astronomers call the KBC Supervoid, an immense underdense region of the universe, billions of light years across, inside which, quite remarkably, we live. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these calm explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always a joy to see our constellation of listeners scattered across the planet, each in their own little corner of space and time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's begin our gentle journey together. And if your mind starts to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Picture yourself lying under a dark sky, the kind where stars don't just sparkle, they feel infinite. You breathe slowly, and for a moment you imagine the space between those stars, that invisible fabric stretching silently in every direction. Astronomers once thought this vastness was perfectly even, that if you could drift far enough, every patch of universe would look like every other. But now, we've learned that the cosmos is not so uniform. It has texture, threads and gaps, clusters and voids, like a sponge carved out of galaxies and emptiness. And somehow our home, the Milky Way, the local group, the Laniakea supercluster, seems to sit inside one of the largest empty regions ever discovered. A place so spacious that even light seems to take a breath before crossing it. They call it the KBC Supervoid, after three astronomers, Keenan, Barger and Cowie, who mapped it for the first time in 2013. Imagine the universe as a loaf of bread, rising gently in the cosmic oven of time. If it were perfectly even, every slice would look the same, stars and galaxies spread like sesame seeds. But the KBC Supervoid is like finding an enormous air bubble baked into that loaf, 2 billion light years wide. Inside this bubble, the average density of matter, stars, galaxies, gas and even dark matter is roughly 20% lower than elsewhere. That may not sound like much, but on the scale of the universe, it's an astonishing dip. Like discovering an ocean where you expected a continent. And we, without realizing it, have been living inside this great hollow for as long as we've looked at the stars. For decades, scientists believed the cosmos obeyed something called the Cosmological Principle, a polite assumption that no place in the universe is special, that from any vantage point the grand picture would look the same, homogeneous, isotropic, evenly sprinkled with galaxies. It's a comforting thought, almost philosophical, the idea that we are not privileged observers, merely part of a grand average. But if we are truly inside a supervoid, that neat picture wobbles a little. It means our measurements, our maps, even our sense of cosmic balance might be tilted by the emptiness that surrounds us. We may have mistaken the calm of our hollow neighbourhood for the calm of the universe itself. The discovery unfolded quietly, not through one telescope or a single revelation, but through decades of counting galaxies. Astronomers gathered redshift data, tiny shifts in light that tell us how far away galaxies are and how fast they move. When the data was plotted, something strange appeared. The density of galaxies, those glittering islands of stars, dropped steadily as the distance increased out to roughly 1 billion light years, then slowly rose again beyond 2 billion. It was as if our cosmic surroundings had been gently scooped out, an underdensity, wide and smooth, encompassing not just our galaxy, but many of our neighbours, Virgo Cluster, Laniakea, even parts of Hydra Centaurus, a hollow yet not completely empty, more like a soft thinning of existence. You might wonder, How could we not notice we were inside something so vast? The answer is as delicate as the phenomenon itself. The void doesn't announce itself. It doesn't pull things inward like a black hole, nor does it leave a clear edge you can see. It's not a hole in space. It's a region of gentler gravity. Galaxies still drift through it, but they do so with slightly different motion, as if the cosmic floor beneath them were subtly tilted. To us, within it, everything feels normal. Only by comparing distant regions can we sense the imbalance, like feeling a faint breeze only when you step outside a sheltered valley. In the standard model of the universe, what cosmologists call the lambda cold dark matter model, such a massive smooth underdensity should be extraordinarily rare, a 1 in 1,000 event, maybe even less, yet here it is. We didn't have to peer across the universe to find it. We simply looked around. Some have argued that our discovery of the KBC Supervoid is just cosmic coincidence, a quirk of where we happen to exist. Others see it as a sign that our cosmic recipe might need refining. Perhaps the ingredients, dark matter, dark energy, gravity itself, behave a little differently than we thought. But for most of us, beyond the mathematics, there's something quietly beautiful in this finding. The idea that our home sits in a kind of cosmic clearing, a tranquil hollow amid the crowded forest of galaxies. It explains perhaps why the night sky feels so spacious. Why, when we look out, the universe seems to drift away faster than expected. Maybe that's because we're measuring from the middle of a gap, and in gaps, space expands a little more freely. If you close your eyes, you can almost sense it. Not the stars, but the space between them. The calm pressure of dark energy breathing through the void. The faint hum of gravity, lessened but still present, keeping the rhythm of motion. We live in that balance, not at the center of the universe, but in a center of quiet. A region so vast that even light takes hundreds of millions of years to cross from side to side. It doesn't change our place in the cosmos, but it adds a layer of wonder. Because if we truly live inside a cosmic hollow, then emptiness isn't absence. It's part of the design. So tonight, as you listen, maybe let your imagination drift a little farther than the stars you know. Picture the universe not as crowded chaos, but as a gentle pattern of fullness and quiet. Filaments of light and pools of calm woven together in silence. Somewhere within that pattern, our galaxy glides, small, luminous, and deeply at peace, inside the quiet center of nowhere. Imagine trying to understand the shape of a fog by counting how many fireflies you can see through it. That's what astronomers do when they map the large-scale structure of the universe. They can't touch it, they can't see the airless space between galaxies, but they can measure the faint points of light, each a galaxy, a swarm of hundreds of billions of stars, and track how those lights are distributed across unimaginable distances. Over decades, astronomers have gathered these cosmic fireflies into enormous catalogues, each one recording where the light comes from, how bright it is, and how its colour stretches ever so slightly toward the red. That stretch, known as redshift, reveals how far away the galaxy is and how quickly it's drifting as the universe expands. In 2013, 3 astronomers, Ryan Keenan, Amy Barger and Lennox Cowie, combined the data from multiple galaxy surveys to see how dense our cosmic neighbourhood truly was. They used about 35,000 galaxies as signposts, each one a marker of mass and light in the universe around us. When they plotted the galaxies' distances and compared the results to what the average universe should look like, they found something extraordinary. Across a sphere almost 2 billion light-years wide, the number of galaxies was about 20% lower than expected. It was as if someone had carved a great hollow into the fabric of the cosmos and placed us quietly inside it. Now, 20% might sound small, but when it comes to the cosmos, even a slight imbalance can echo through everything we observe. Imagine listening to a symphony and realizing that one entire section of the orchestra is playing just a touch softer. The overall melody is still beautiful, but the harmony changes in subtle ways that ripple through every note. That's what an underdense region does to the symphony of the universe. It slightly alters how galaxies move, how space expands, and how light reaches us from distant pasts. To grasp the scale of this discovery, it helps to think about what 2 billion light-years means. Light, which travels at almost 300,000 kilometers per second, would need 20 human lifetimes, not of years, but of entire civilizations, just to cross it. This hollow is not a local gap like a missing star cluster. It's a continent-size emptiness in the ocean of space, and we're sailing right in the middle of it, without realizing the water is thinner here. The team compared their results to the standard cosmological model, often called the lambda-cold dark matter model, a name that sounds intimidating but simply describes a universe filled mostly with invisible matter and a smooth, accelerating energy that stretches space itself. In simulations based on that model, voids do appear, but smaller ones may be a few hundred million light-years across. A structure as large and smooth as the KBC region is expected to be exceedingly rare. Some estimates say a 1 in 10,000 event, and yet here it is, surrounding our entire galactic neighborhood. To test whether this apparent void was real, scientists turned to independent measurements. They looked at the number of galaxies in the infrared, where dust and bright young stars can't hide their true count, and still found the same pattern: a steady dip in density near our position, followed by a gradual return to normal farther away. They also studied how galaxies were moving. Inside the KBC region, galaxies appear to be drifting outward a little faster than average, like dust grains caught in a gentle cosmic breeze. Beyond the edges of the void, that motion slows, then settles. It's as though space itself is breathing more freely here. At first, many astronomers were cautious. Could this be a trick of perspective, a statistical fluke, or even a bias in how we observe the sky? After all, our instruments are far from perfect, and the universe has a way of hiding its patterns beneath random noise. But over the following years, other surveys confirmed similar trends. Maps from the 2-micron All-Sky Survey, the Sloan Digital Sky Survey, and the Cosmic Flows Velocity Field all pointed toward the same conclusion. Our corner of the cosmos really is lighter, less crowded, a little more hollow than average. It's tempting to picture a void as pure emptiness, but that isn't quite right. Inside, galaxies still exist, delicate spirals, dim dwarfs, islands of light, just fewer of them. The space between is wider, the gravitational pull weaker. It's like walking through a forest where the trees grow thinner and the air feels broader somehow. You can still hear the wind between the branches, but there's more sky in every direction. And that extra sky, that faint looseness, might explain some of the universe's current mysteries. When we measure how fast the cosmos expands, something we call the Hubble constant, we do it by watching how distant galaxies recede from us. But if we're inside a bubble of a low density, then our local region is expanding a little faster than the cosmic average. It's like measuring the speed of a river while standing in an eddy. The water around you might move faster or slower than the main current. This could be one reason why local measurements of the Hubble constant give a higher value, around 73 kilometers per second per megaparsec, than the cosmic microwave background suggests, which is closer to 67. The difference, about 9%, is known as the Hubble tension, and the KBC Supervoid may be quietly tugging at that string. But beyond numbers and debates, there's a humbler realization. We humans, perched on a small planet circling an ordinary star, are inside a very special kind of stillness. Not a privileged position, but a poetic one. We occupy a cosmic hollow that has shaped our view of the universe, softened its expansion, and perhaps even guided the way we interpret its beginnings. The space we thought was uniform has revealed a hidden asymmetry, not because we looked for it, but because we finally counted carefully enough to see it. And if you imagine drifting outward through this void, it wouldn't look empty. It would look peaceful. Galaxies would thin. The web of cosmic filaments would fade into soft strands, and beyond, the density would rise again. A subtle gradient in the grand painting of space. There's a certain serenity in that pattern, a rhythm to existence that alternates between presence and absence, between light and the silence that gives light room to shine. So when we say we live inside a supervoid, we're not talking about something fearful or cold. We're describing a kind of cosmic valley, a wide, tranquil depression in the landscape of matter. The discovery of the KBC region doesn't diminish the beauty of the universe. It enriches it. It reminds us that even in the largest scales, nature prefers variation, texture, imperfection, the subtle differences that make every view unique. The stars still glow, the galaxies still spin, and the universe still sings its ancient song. We've simply learned that the part of the song we hear best comes from a quieter chamber of the hall. When you look at the night sky, it's easy to think of the universe as something static, a grand, frozen mural of stars scattered across the dark. But it isn't frozen at all. Every point of light you see is moving away from every other, carried along by the quiet expansion of space itself. This expansion is what astronomers measure when they talk about the Hubble constant, a gentle rhythm describing how many extra kilometers of separation appear between galaxies for every million light-years of distance. It's the cosmic breath of the universe, steady, patient, and ongoing. For most of the last century, scientists believed they understood that rhythm fairly well. When they looked deep into space, toward light that had travelled for billions of years, they found that the universe expands at roughly 67 kilometers per second for every megaparsec, which means about 3 million light-years. But when they measured galaxies close to us, using nearby supernovae and variable stars as distance markers, they found a faster tempo, about 73 kilometers per second. The difference may not sound large, only a few percent, but in cosmology it's enough to set off alarm bells. That small mismatch between the early universe rhythm and the local one is what astronomers now call the Hubble tension. It's a bit like listening to a familiar song and realizing two musicians are playing it in slightly different keys. They're both following the same sheet music, but something between the first note and the last has shifted. To some scientists, this discord hints that the physics of the universe may have changed over time. Perhaps dark energy evolved, or gravity behaves differently than we expect on very large scales. But others suspect that the discrepancy may come from our vantage point itself. Maybe we are hearing the song from inside a hollow hall, where the acoustics change the sound ever so slightly. If we truly live inside the KBC Supervoid, a region with less matter than the cosmic average, then space around us should be expanding a little faster than space in denser areas. You can picture it as air trapped inside soap bubbles. The thinner the walls, the quicker the bubbles grow. The galaxies near the centre of a void are carried outward by a slightly stronger local expansion, while those beyond its edge feel the slower tug of gravity from the surrounding cosmic web. From inside, the whole universe seems to be pulling away more quickly, even though the overall cosmic tempo hasn't changed. When astronomers model this effect, they find that a void about 2 billion light-years wide and about 20% underdense could make the local Hubble constant appear higher by roughly the amount we observe. In simpler words, if we live in a thinner part of the cosmic fabric, our own corner of space is stretching faster than the average. Beyond the void's edge, the pace returns to normal. It's as if the universe were quietly exhaling a little faster here, only to catch its breath farther out. To understand this more intuitively, imagine standing on a hillside during a light rain. If the ground beneath your feet is tilted slightly, the raindrops seem to fall in one direction faster than another. But from a distance, the rainfall is uniform. Your local slope gives you a skewed sense of the pattern. In the same way, our cosmic slope, the underdensity of the KBC region, gives us a local bias when we measure how, fast galaxies recede. We think the universe is sprinting when, in truth, we're standing on uneven ground. This idea isn't just a mathematical curiosity, it has real, measurable consequences. If the KBC void is responsible for part of the Hubble tension, then the rate of expansion we measure should change gradually with distance. Closer galaxies would show a faster expansion. Beyond about 2 billion light-years, the rate should flatten to the lower global value. Astronomers have looked for this trend, and some data do hint at exactly that pattern, a fall-off of a few percent as you move beyond the void. But the evidence is still gentle, still uncertain, like the first ripples of a wave just beginning to form. What makes this picture so haunting is its subtlety. The universe doesn't mark the boundary of the void with a line or a colour. There's no sign saying, "Here the density returns to normal." Instead, gravity and light weave their hints together quietly. Galaxies just beyond our region drift a bit slower, while those within move a bit faster. If you could watch this over billions of years, you'd see the walls of the void slowly expand, the filaments at its edges pulling gently inward, and everything inside drifting outward. Not explosively, but gracefully, like the slow rise of bread in a still oven. Some researchers argue that even such a large void cannot fully explain the tension, that we would need an emptiness too extreme to be realistic. Others counter that we may not need a perfect match. Only part of the discrepancy may come from our local environment, with the rest arising from measurement details or calibration differences between instruments. The truth is likely a combination of both. A small systematic uncertainty, amplified by the quiet effect of our cosmic hollow. Either way, the lesson is profound. It reminds us that our observations are never completely detached from where we stand. Just as a sailor's map depends on the depth of the sea beneath the hull, our cosmic measurements depend on the density of the universe beneath our galaxies. We are part of the system we measure, entwined in the very expansion we seek to describe. The KBC void doesn't just reshape equations, it reshapes perspective. There's something gently humbling about that. We once imagined ourselves at the centre of everything, then learned we orbit an average star in an ordinary galaxy. Now we discover that even the space surrounding that galaxy is not entirely ordinary. It is a rare bubble, a softly underfilled region floating in the cosmic foam. And somehow, that seems fitting. It means that even in the larger scales, the universe carries the same signature it does on smaller ones. Variation, unevenness, individuality. The grand design is textured, not plain. So when astronomers say we may be measuring from a hole, they don't mean we've made a mistake. They mean we've uncovered another layer of truth. Our cosmic neighbourhood is not an average patch of reality, but a quieter one, where expansion moves with a touch more freedom and light travels through a little more stillness. To measure the universe from here is to listen from inside a vast and echoing hall, where every sound is softened by the space around it. And perhaps that's what makes our view so beautiful, that in trying to measure everything outside of us, we also learn something about the place we call home. The numbers we find are not wrong, they are simply whispered through the acoustics of our cosmic chamber. Imagine for a moment that space itself could bend, not just in the way light curves around stars, but in the quiet way fabric stretches when it's missing a little weight. This is what happens inside a cosmic void. The geometry of space, its shape, its internal tension, changes when there's less matter to anchor it. Where there's plenty of mass, gravity tightens the weave of the universe, pulling threads inward and slowing expansion. But in a region where galaxies are sparse and gravity is weaker, those same threads relax. Space expands a little more freely, time runs a touch differently, and the distances between everything grow faster than they do elsewhere. You can picture this by imagining a vast elastic sheet. If you set a heavy ball on it, the sheet dips and curves inward. That's gravity creating its familiar pull. But what if, instead of a ball, you remove material from underneath? The fabric would bow outward, ever so slightly. A void behaves like that, not by pulling things in, but by releasing them outward. A gentle exhale in the cosmic structure. It doesn't break the universe's geometry, it just changes the local balance between mass, energy, and the constant pressure of space itself. Inside the KBC Supervoid, this outward curvature is subtle yet important. Over hundreds of millions of light years, it creates a small difference in how galaxies move. If you could draw their paths on an invisible map, you'd see the orbits stretch outward like faint ripples. Closer to the void's centre, space expands a bit faster. Near the edges, where matter begins to thicken again, the pace slows, almost as if the galaxies are gliding up a gentle slope of gravity. To us it feels seamless, because the change happens over such enormous scales. But to precise instruments, the telescopes measuring redshift and brightness, the slope is there, and it tells us something extraordinary about the shape of where we live. The geometry of emptiness also changes how light itself travels. When a beam of light moves through a dense region, it feels gravity's pull. The photons lose a bit of energy climbing out of the curvature caused by matter. Inside a void, the opposite happens. The light moves through a region of less curvature, gaining just enough breathing room to stretch a little more freely. When that light finally reaches us, it carries the faint signature of the void it crossed. That's part of why the universe's background glow, the ancient microwave light from the Big Bang, shows tiny cool spots that align with large underdense regions. The light didn't cool because of temperature in the usual sense, but because it passed through a zone where space was expanding slightly faster. Each photon was stretched like a violin string tuned just a little looser. When astronomers talk about these effects, they sometimes use symbols that look daunting. Equations tying curvature to density, density to expansion, and expansion to time. But in simple terms, all of it comes down to a balance. The universe behaves like a vast seesaw between matter, which pulls inward, and dark energy, which pushes outward. In regions like the KBC void, the pulling side is lighter, so the pushing side wins a little more often. Over billions of years, that imbalance becomes measurable, a quiet acceleration written into the very coordinates of space. Now, you might ask, if the universe is supposed to be homogeneous on large scales, how can such an uneven patch exist without breaking the rules? The answer lies in how we define large. On the scale of hundreds of millions of light years, the cosmos is indeed lumpy, filled with filaments, clusters, and empty basins. But when you step back far enough, across tens of billions of light years, those lumps average out. The KBC Supervoid doesn't overturn the cosmological principle. It just reminds us that even smoothness, in nature, is statistical. The universe doesn't have to be uniform everywhere at once. It only needs to be balanced in the long run. Still, this balance creates fascinating consequences for how we see time. Because gravity and curvature are linked to the flow of time itself, clocks inside a deep void would tick ever so slightly faster than those in denser regions. The difference is tiny, a fraction of a second across millions of years, but it's real. Time in a void stretches with space. The emptier the environment, the less resistance time encounters as it passes. It's a thought that feels almost poetic. In emptiness, not only distance expands, but moments too. Astronomers test these geometric effects by comparing distant measurements of the Hubble constant with nearby ones, tracing how the rate of expansion changes with depth. If our universe were perfectly uniform, the expansion rate would be the same everywhere. But observations show a gentle variation, faster nearby, slower farther out, just what you'd expect if we were observing from within an underdense bowl. This Hubble bubble view doesn't require new physics. It arises naturally from the geometry of emptiness itself. The universe hasn't changed its laws, We're simply sitting in a place where those laws produce a slightly different melody. Over the next few years, new instruments will test this idea with remarkable precision. The DESI survey, the Rubin Observatory and the European Euclid mission are designed to map galaxies and cosmic voids in exquisite detail, tracking how light bends, stretches and fades across billions of years of cosmic history. If the KBC Supervoid truly shapes our local expansion, these projects will see its fingerprint, a faint symmetrical dip in density surrounding our position, blending into the denser walls beyond. If they don't find it, we'll know that something even stranger must be at work. Either way, the geometry of emptiness will have taught us something profound, that even the absence of matter carries form and structure, that nothingness itself has shape. To live inside such a structure is both humbling and comforting. It means we're part of a region where space breathes more freely, where galaxies glide a little faster, and where the light that reaches us has travelled through the universe's most tranquil halls. When we measure the cosmos from here, we're measuring through that stillness, and maybe that's what makes our observations, our maps, our values, our cosmic constants, so beautifully human. They're shaped, as we are, by our surroundings. If you could step outside the void, watching from its rim, the difference would be invisible to your eyes. The stars would look the same, the galaxies just as bright. But in their motion, in their faint redshifts and subtle drifts, you'd see the pattern, a gentle outward breath, a bubble of low gravity expanding within the greater web. That's where we are. Not in the middle of everything, but in the soft curvature of less. The universe has allowed us a quiet corner from which to watch it grow, and in that corner, even emptiness becomes a kind of grace. If you could drift far enough above the universe and look down, the view would surprise you. You wouldn't see a solid fabric of stars stretching evenly into the distance. You'd see structure, a vast cosmic lacework made of threads and hollows, filaments and empty rooms. Astronomers call this the cosmic web, and it's one of the most beautiful and humbling things we've ever discovered. Galaxies don't scatter randomly. They gather into clusters, then into long glowing strands that crisscross space like illuminated bridges. Between these bridges lie enormous gaps, the voids. At first, the idea that the universe is mostly empty feels wrong. After all, when we look at the night sky, it seems full of light. But the truth is, light comes from the few places that are not empty. On average, about 90% of the volume of the universe consists of voids, and only the remaining 10% forms the luminous web that holds the galaxies. It's like looking at a city from space at night. The roads are dark, the neighbourhood's quiet, but every now and then a glowing cluster marks a living centre. The light isn't everywhere, it simply outlines the invisible framework beneath. The cosmic web emerged naturally as the universe expanded from its hot beginning. In those first moments, matter wasn't perfectly smooth. Tiny ripples of density, 1 part in 100,000, grew under the influence of gravity. The slightly denser regions attracted more material, forming knots and filaments. The slightly emptier regions lost their matter to those growing structures, becoming emptier still. Over billions of years, this process turned the early fog of hydrogen into a delicate network. Dense filaments surrounded by great cavities, like soap bubbles pressed together in 3 dimensions. The largest of these cavities stretch hundreds of millions, even billions of light years across. The KBC Supervoid is one of them, but it's not alone. Surrounding it are other large basins, the local void, the Eridanus Supervoid, and the farther ones that form part of a repeating cosmic pattern. Each void is a quiet chamber between walls of galaxies. Inside, gravity is weaker, so space expands a bit faster. Outside, in the dense filaments, galaxies pull together, slowing expansion, and sometimes merging in vast collisions. The result is a cosmic rhythm, emptiness pushing outward, matter pulling inward, both in perfect counterpoint. Astronomers model these voids not with equations full of symbols, but with imagery of motion, tiny arrows showing the direction in which space itself flows. In dense regions, arrows converge, in voids they diverge. The cosmic web breathes. Filaments act like the bones of a living creature, and voids are the lungs between them. When you step back far enough, you can almost sense the pulse, not of life as we know it, but of balance, of tension and release written into the architecture of the cosmos. What's fascinating is that voids come in layers, like nested bubbles. Our own local void, roughly 300 million light-years wide, sits inside the greater KBC region, which is almost 2 billion light-years across. Beyond that, the cosmic web continues with other voids and superclusters, interlocking like cells in an endless honeycomb. We live not in one empty room, but in a suite of them, an entire neighbourhood built of space and silence. The local void influences how our nearby galaxies move. The KBC Supervoid influences how we measure cosmic expansion, and the whole lattice of voids and filaments defines the shape of the observable universe. From our perspective, all of this structure might seem static, but it's not. Voids grow. As time passes and dark energy continues to accelerate expansion, these low-density regions stretch, merging with neighbours like air pockets combining into larger bubbles. The filaments between them become thinner, the galaxies more isolated. In a distant future, long after the Milky Way has merged with Andromeda, the surrounding universe will look far emptier than it does now. The cosmic web is evolving toward an ever lighter texture. You just web fading into transparency. This dynamic has a remarkable implication. Inside a void where matter is scarce, dark energy dominates sooner. The push of expansion overtakes the pull of gravity much earlier than in denser regions. That means voids act as early laboratories for the future of the universe. They are previews of what the cosmos as a whole will become billions of years from now, smooth, stretched, and quiet. In a sense, our region offers a glimpse into tomorrow's universe. We live in a place where the future's physics arrives a little ahead of schedule. Astronomers explore this architecture by studying how galaxies cluster along different lines of sight. In three-dimensional maps, voids appear as pale hollows surrounded by bright filaments. Some are spherical, others irregular. The KBC Supervoid stands out because it's so vast and so gentle. Not an abrupt emptiness, but a slow decline in density that blends seamlessly into the walls beyond. It's like a valley carved not by erosion, but by the absence of pressure. There are no sharp edges, only gradual transitions. We often think of emptiness as nothing, but in cosmic terms, emptiness has identity. It shapes the motion of galaxies, alters the flow of time, and even affects the temperature of the oldest light. When the cosmic microwave background radiation travels through a void, it slightly loses energy, producing those faint cold spots we observe in the sky. So even where there is almost nothing, there is still an effect, a fingerprint of existence. The architecture of voids proves that nothingness is not truly nothing. It's a framework for everything else. And there's another subtle beauty, the symmetry between small and large. The shapes we see in the cosmic web mirror patterns found in rivers and roots, in frost on a window pane, in neurons inside the brain. Nature builds with the same instincts across scales. The same physics that draws galaxies into filaments also sculpts clouds, mountain ridges, and coral reefs. Each follows the quiet mathematics of connection and separation, the dance between attraction and expansion. The universe is not random chaos. It is ordered complexity, built from repetition and variation. When you look up tonight, the stars you see belong to one thread in that infinite tapestry. They sit on a filament of the cosmic web that traces the boundary of our void. Beyond them lies the soft darkness of the KBC region, spreading for billions of light years, and beyond that, other filaments, other hollows, an unending alternation of fullness and quiet. It's easy to feel small when thinking about such scales, but perhaps that's not the point. Perhaps the wonder lies in realizing that we're part of that pattern, creatures of light living in a momentary pause between the universe's inhalations and exhalations. So, when astronomers speak of voids, they're not talking about places to fear. They're describing the geometry of peace, the vast spaces that give meaning to the galaxies between them. Every cluster of stars owes its clarity to the void beside it, just as every note in a song depends on the silence that follows. The universe is not one endless explosion of matter, but a balanced composition of something and nothing, woven together by time. And in our little corner of that design, we rest within the quiet, intricate architecture of the void. When you step outside on a calm day, you might feel that the air is still, but if you watch the clouds long enough, you realize that everything is moving, not fast, not chaotic, but in slow, graceful motion. Galaxies too drift like those clouds. Even as the universe expands overall, each galaxy carries its own quiet motion through the cosmic air, a motion astronomers call peculiar velocity. It's not peculiar because it's strange, but because it's personal. It's the motion that belongs to a galaxy itself, separate from the expansion of space. Our Milky Way is no exception. For all our sense of cosmic stillness, our galaxy is actually speeding through the universe at about 600,000 miles per hour. You don't feel it, of course. Everything nearby, including the Earth, the Sun, and the neighbouring galaxies of the local group, shares that same immense glide. There's no wind, no resistance, only the silence of motion through the largest emptiness imaginable. But what sets us moving in that particular direction, and at that astonishing speed? The answer, like so much in cosmology, lies in balance, the push and pull between what is present and what is missing. On one side of our cosmic neighbourhood lies the local void, a relatively empty expanse about 300 million light-years wide. On the other side lies the Virgo cluster, and, farther beyond it, the enormous concentration of galaxies called the Great Attractor. Our galaxy, along with thousands of others, sits on a thin, luminous bridge of matter between these regions, a flattened structure astronomers call the local sheet. You can imagine this local sheet as a raft of galaxies floating on a gentle current. On one side, the water pulls away, draining toward the hollow of the local void. On the other, the current tugs toward the Great Attractor. The raft drifts between these influences, tilting slightly toward the denser region, but also pushed outward from the emptier one. In measurable terms, the local sheet is receding from the local void at roughly 260 kilometers per second, while the Virgo cluster pulls us with nearly 250 kilometers per second in the opposite direction. When combined, these motions, along with a few smaller contributions, yield the total velocity of about 627 kilometers per second relative to the cosmic microwave background. It's a number too large to picture, but we can soften it into an image. Imagine floating inside a warm ocean, feeling two vast, slow currents meeting beneath you. One draws you gently forward, the other presses you back. The water doesn't churn, it glides. The universe moves like that, steady, directional, serene. These cosmic flows, as astronomers call them, are like the heartbeat of large-scale structure. They trace the gravitational landscape of the universe. Matter flows toward the dense ridges of the cosmic web and away from the hollow basins. The boundaries between voids and clusters act like invisible shorelines. Our local sheet is one of those boundaries, balanced between emptiness and attraction. Within it, galaxies share a coherent motion, travelling together for hundreds of millions of light-years as if tied by an unseen current. This idea of coherence is important. It means that the Milky Way doesn't wander through space alone. For as far as we can map, hundreds of millions of light-years, other galaxies share roughly the same direction and speed of motion. Astronomers call these vast patterns bulk flows. They're not random drift, but organised motion, the result of the combined gravity of everything in our region of the cosmic web. Some models predict that these flows should fade at great distances, blending into the overall expansion of the universe. Yet, intriguingly, we still detect them even farther out, hinting that the gravitational imbalances extend over scales larger than we once imagined. In 2014, researchers from the Cosmic Flows Project mapped these motions in 3 dimensions and found that our local sheet is part of an even grander structure, the Laniakea supercluster. Laniakea, a word from Hawaiian meaning immeasurable heaven, spans about 500 million light-years and contains over 100,000 galaxies. It's not a cluster in the tight sense, but a gravitational basin, a region where flows of galaxies converge toward a common centre. Beyond its edges, those flows point elsewhere, toward other superclusters and deeper cosmic valleys. It's as if the universe were divided into great watersheds of motion, each one a separate catchment area in the landscape of gravity. Laniakea itself drifts gently inside the larger KBC region, which means our whole supercluster participates in the expansion of the surrounding void. The galaxies at its outer edges feel the faint outward pull of the underdensity, while the inner ones respond to the attraction of nearby concentrations like the Shapley supercluster. It's a delicate balance. Push and pull, attraction and release, playing out across scales of billions of light-years. From our human vantage point, these motions are almost incomprehensible. We think of movement as something you can feel, but here, motion is absolute stillness. The galaxies flow through space not by crossing it like boats through water, but because space itself stretches and carries them along. In this sense, our velocity is not a journey through the universe. It's a property of the universe's own breathing. Every region has its tempo, and ours happens to be a little quicker, shaped by the geometry of the void we inhabit. Astronomers sometimes illustrate these flows with colour maps, blues for approaching regions, reds for receding ones. When you look at such a map, the KBC region appears as a vast pale area where arrows point outward, away from the centre. It's the cosmic equivalent of a slow breeze rising through an open field. The walls of the void are outlined by clusters and superclusters, each marking the boundary where gravity begins to dominate again. Our galaxy sits not at the exact centre, but well within this hollow, moving calmly with its neighbours toward the richer regions ahead. There's something deeply soothing about this realisation. The Milky Way's path, immense as it is, feels almost meditative. It's a motion without struggle, guided by forces that have shaped the cosmos since its birth. Even in motion there is peace, a sense of being carried. When you look at the stars tonight, you can remember that they too are moving, not randomly, but as part of a slow choreography written into the fabric of the universe. So the next time you feel still, remember that stillness is an illusion. Beneath it, you're drifting with your planet around the sun, with the sun around the galaxy, with the galaxy through the void, and with the void itself through the larger cosmos. Each of these motions is part of a greater flow, a seamless current that began billions of years ago and will continue long after we're gone. We are, all of us, passengers on this quiet tide, carried by the geometry of space, drawn by the pull of distant clusters and gently pushed by the hush of emptiness that surrounds us. The great flows remind us that even within the vast silence of the universe there is rhythm. It may not be a rhythm we can hear, but it's one we can feel, not in our bodies, but in the understanding that everything moves together. The stars, the galaxies, the light, and the empty dark between. All part of one immense, graceful drift through the quiet sea of space. Every sound leaves a pattern, even if it travels through silence. If you could listen to the early universe, not with ears, but with instruments tuned to light, you would hear it humming. not loudly, not violently, but as a series of faint ripples spreading through a sea of hot hydrogen and helium. These ripples are the first whispers of structure, the echoes of pressure waves that rippled through the young cosmos more than 13 billion years ago. Astronomers call them baryon acoustic oscillations, a name that sounds far less poetic than the thing it describes. Imagine the universe when it was still a glowing fog so dense that light couldn't travel freely. Gravity pulled matter inward, while radiation pushed it outward. The result was a constant rhythm, compressions and rarefactions like the surface of a pond disturbed by countless overlapping waves. When the universe cooled enough for light to break free, those ripples froze into its structure. They became the preferred spacing between galaxies, a faint memory of ancient sound. Today, that distance, roughly 500 million light-years, acts like a cosmic ruler. No matter where we look, galaxies show a slightly higher chance of being found about that far apart. It's as if the universe remembers its first song, and we can still trace the beat. Astronomers measure this pattern to understand how the cosmos is stretched over time. If space expands faster, the apparent scale of these ripples grows. If it expands slower, it shrinks. By comparing this scale at different distances, scientists can test whether our local neighbourhood, the KBC Supervoid, truly expands faster than the rest. Inside the void, the clustering of galaxies appears slightly weaker. The ripples seem stretched, the ruler subtly longer. This suggests that space within our region has expanded more, just as the void hypothesis predicts. But even this difference is gentle, only a few percent, barely enough to see without precise instruments. And yet, that tiny variation holds clues to one of the biggest mysteries in cosmology: why our measurements of expansion disagree depending on where and how we make them. To detect these ripples, researchers use enormous surveys like Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument, mapping millions of galaxies across the sky. When the data are plotted in 3 dimensions, patterns emerge, faint waves in the density of matter, alternating bands of more and less populated regions. The KBC Supervoid shows up not as a sharp gap, but as a long, graceful trough in that landscape, a region where the cosmic waves have stretched farther apart. It's like finding a subtle change in the tone of an ancient instrument, not enough to rewrite the melody, but enough to make you wonder if the room itself affects the sound. And there's another kind of light that carries information even older: the cosmic microwave background. This faint radiation, discovered in 1965, is the afterglow of the Big Bang itself, still washing over us from every direction. It's incredibly uniform, but not perfectly so. If you map it carefully, you see faint mottling, regions a little warmer, a little cooler. These variations reveal the universe's structure at a time when it was only 380,000 years old. They are quite literally the fingerprints of creation. Now, light from the cosmic microwave background doesn't just travel in straight lines forever. On its long journey to us, it crosses clusters, filaments, and voids, gaining and losing energy along the way. One particular effect, known as the integrated Sachs-Wolf effect, occurs when light passes through a region of changing gravitational potential. In a dense cluster, photons fall in and climb back out, losing a bit of energy but ending up nearly unchanged. In a void, however, space expands faster while the light is inside. The gravitational well shallows before the photon can climb out, leaving it with slightly less energy, which we see as a tiny drop in temperature. It's a minuscule difference, just a few millionths of a degree, but across the sky, patterns begin to emerge. When astronomers align maps of known voids with maps of the cosmic background, they find that these voids often coincide with cold spots. One of the largest and most famous is the Eridanus Supervoid, which overlaps with a region of the microwave background that appears unusually cool. Some scientists think this alignment is a coincidence. Others see it as evidence that the voids truly shape the oldest light in the universe. Either way, the connection between structure and shadow is undeniable. Even nothingness leaves its mark. If you imagine a photon, a single particle of light, leaving the early universe and travelling across billions of years, its journey would be shaped by these landscapes of gravity and emptiness. It would weave through clusters where space is tight, then glide through voids where space relaxes. Each time, it would change ever so slightly, like a tone shifting as it echoes through different halls. When that photon finally reaches our telescopes, it carries with it the record of every shape it has crossed. In a sense, the cosmic microwave background is a diary written in light, a diary in which even the blank pages, the empty regions, have stories to tell. What's astonishing is how all these pieces fit together. The faint ripples in galaxy spacing, the smooth cooling of the cosmic background, the outward drift of galaxies within our void. They all echo the same pattern. They tell us that emptiness isn't inert. It expands, it breathes, it interacts with light. Space isn't a neutral backdrop for the universe, it's a participant. Its geometry and energy define how everything else moves. The KBC region may be a place of less matter, but it's also a place where the universe's grand design becomes visible in its simplest form. Expansion itself, unmasked by gravitational clutter. To see that connection is to understand the cosmos in a new way. We are not separate from the voids, we are shaped by them. Our measurements, our view of the sky, even our understanding of cosmic time, are filtered through these immense hollows. They are the quiet spaces between the notes, the pauses that give meaning to the cosmic melody. When we study their ripples and their shadows, we are reading the universe's music in reverse, from the lingering echo of its first song. And perhaps that is what makes this work so quietly beautiful. The story of the KBC Supervoid isn't about darkness swallowing light. It's about how absence can reveal structure, how silence can carry sound, the faint cooling of the cosmic background, the stretched spacing of galaxies, the slow outward flows of matter. All of it forms one consistent whisper, one long exhale of creation. Somewhere within that breath, we are listening, floating inside the stillness, tracing ripples that began before time had a name. Light is one of the most obedient things in nature. It travels straight, without hesitation, and at a constant speed that no force can truly stop. Yet it's not immune to the shape of space itself. When light passes near something massive, a star, a galaxy, a cluster, it bends. Not because it wants to, but because space around that mass curves, and light simply follows the path that space provides. Astronomers call this bending gravitational lensing. It is the universe's way of revealing its invisible architecture, tracing mass that even our best telescopes cannot see. Usually we think of lensing as something that magnifies, a kind of cosmic magnifying glass. A cluster of galaxies bends the light from more distant ones, stretching and brightening them. But voids, the great empty regions between those clusters, do the opposite. They act not as magnifying lenses, but as soft diffusers, spreading the light and making distant galaxies appear slightly dimmer and smaller than they would otherwise be. Where mass curves space inward, emptiness curves it outward. Imagine light as a flock of birds flying in perfect formation. When the flock passes over a valley, the pattern stays tight. But when it crosses a hill, the birds spread out, their paths diverging. A void is that hill in the geometry of space. The light entering it spreads just a bit more, arriving on Earth with a subtle difference that only careful observation can reveal. This effect is extremely gentle, far weaker than the lensing caused by clusters, yet it's measurable. Astronomers have spent years stacking the light from thousands of voids to amplify the signal, combining many faint distortions into one clear pattern. What they find is consistent and unmistakable. Lines of light slightly diverge as they pass through these vast hollows. The background galaxies seen through a void look just a little smaller, their light fractionally cooler, as if the universe itself took a deeper breath along that line of sight. In 2016, researchers studying the cosmic voids detected this anti-lensing more clearly than ever before. By comparing the brightness and shape of distant galaxies, they confirm that the empty spaces are not truly empty. They have their own gravitational fingerprints, negative images of the dense filaments surrounding them. When they plotted these effects on maps, the voids appeared as pale, almost ghostly regions where light's path diverged. The cosmic web looked like a network of faint glowing lines suspended in mist, with darkness not as absence, but as structure. Inside the KBC Supervoid, these effects are too subtle for the naked eye, but strong enough to alter the light we collect from faraway galaxies and even from the cosmic microwave background. When the ancient photons from the Big Bang cross this vast underdense region, they lose a little energy and scatter slightly. By the time they reach us, they carry the signature of the void, a faint smudge of cooling, a gentle defocusing. Some of the most distant galaxies we observe are seen through this layer of expanded space. Their shapes and apparent distances are influenced by the geometry of our hollow cosmic home. If you were to watch this as a slow-motion film, you'd see light entering the void, spreading ever so slightly, and then reconverging as it exits. The journey would take hundreds of millions of years, yet the deflection itself would be almost imperceptible, a fraction of a degree, smaller than the width of a human hair seen from across a room. But these minute differences accumulate across billions of photons, billions of galaxies, and billions of years, creating the soft structure we now call the cosmic web. Gravitational lensing doesn't just show us where matter is, it shows us where it isn't. By measuring how much light bends, or in this case how much it fails to bend, astronomers can map the hidden distribution of dark matter and dark energy. Voids turn out to be powerful laboratories for this work, because they exaggerate the contrast. In the emptiness, even small traces of matter or energy leave distinct marks. It's as if by stripping away the clutter of galaxies, the universe has given us a clearer window into its invisible forces. This discovery ties into something deeply philosophical, the idea that absence can reveal more than presence. In everyday life, it's often the silence between notes that defines the melody, or the space between words that gives language its rhythm. The universe, it seems, follows the same rule. Where there's less matter, the subtle properties of space and time become easier to notice. Voids amplify the whispers of dark energy and the soft contours of gravity in ways that crowded regions cannot. For the KBC region, this means that our cosmic address is not only a curiosity, it's a vantage point. Living inside a supervoid gives us a clearer perspective on the universe's expansion and on the mysterious energy that drives it. We are like observers standing in the centre of a vast, calm lake, able to watch the reflections ripple in all directions without obstruction. It's ironic, but beautiful. The emptier our surroundings, the better they let us see. When scientists describe how light moves through these regions, they sometimes use an equation that relates the curvature of space to the density of matter. The more mass there is, the more space curves inward. The less mass, the more it curves outward. But beyond the mathematics, the essence is simple. Light always follows the straightest possible path, and in an expanding void, the straightest path happens to be through slightly stretched space. As light travels, it experiences the shape of that space directly, like a hand running along the contours of a smooth sculpture. Every photon that reaches our eyes carries a faint memory of these encounters. The starlight you see tonight has passed through countless invisible hills and valleys in space-time, each one altering its journey by the smallest amount. In those deviations lies the record of the universe's structure, not written in ink, but etched in light itself. So when we talk about seeing the invisible, we're not speaking in metaphor. We truly see what cannot be seen. Gravity without matter, curvature without weight, structure without form. The light that fills our telescopes is shaped by the voids as surely as it is by the galaxies. In that interplay of brightness and absence, the universe reveals both halves of itself, the luminous and the hollow, the full and the quiet. And as that light reaches us after billions of years of travel, it carries a story that's still unfolding, a story where even emptiness bends, where nothingness has geometry, and where our own existence depends on the unseen scaffolding of space. Perhaps that's the universe's greatest secret, that to understand its fullness, we must first listen to the soft, invisible shape of its emptiness. In most places across the universe, galaxies live crowded lives. They pull on one another through gravity, collide, merge, and occasionally tear themselves apart. In dense clusters, they whirl like dancers in a tight crowd, brushing shoulders at every turn. But inside a void, in the vast hollowness where the pull of gravity is weak and encounters are rare, galaxies live differently. They grow slowly, quietly, and often alone. Astronomers who study the galaxies that inhabit cosmic voids call them quiet survivors. They are not the grand, elliptical giants we see in crowded clusters. Instead, they are smaller, lighter, and often more fragile. Their shapes tend to be spiral or irregular, and their colours lean toward the soft blues of youth. That blueness is not a trick of light, but a signature of star formation. Blue stars burn hot and live fast, which means these galaxies are still forming new stars even now, billions of years after the universe began to settle. The reason lies in their isolation. In emptier regions, galaxies almost never collide, so they evolve without the violent disruptions that shape their cousins in denser environments. When galaxies merge, their gas clouds compress, igniting bursts of star formation before settling into larger, redder systems. But inside a void, those fireworks seldom happen. Gas clouds remain unperturbed, forming stars only when gravity gently gathers them over time. It's a slower rhythm, less symphony, more steady heartbeat. If you could drift through the KBC Supervoid and visit these galaxies, you would see them scattered like distant lanterns hanging in a vast cathedral of air. Each one glows softly, surrounded by enormous stretches of silence. Their nearest neighbours might be millions of light years away, and yet they keep shining, sustained by the thin reserves of gas that remain in their halos. A galaxy's halo is its invisible cocoon, a sphere of dark matter that holds its stars and gas together. For galaxies in voids, those halos are often small. If their gravitational pull is weaker than about 35 kilometers per second, that's how fast something must move to escape. They struggle to retain their gas. Much of it slips away into the surrounding emptiness. Without that raw material, some halos remain dark, never forming visible stars. Astronomers call them dark galaxies, islands of invisible matter, silent and unseen, detectable only by the faint motions of nearby gas. Yet not all void galaxies are so faint. Some, perhaps because they've managed to hold on to a bit more gas, experience short, unexpected bursts of star formation, quiet hearts that suddenly remember to beat faster. For a few 100 million years, they blaze with new blue stars, then fade again into calm. These bursts seem to happen randomly, but they tell us something important. Even in the loneliest parts of the cosmos, creation is not over. The void may be quiet, but it's still alive. Scientists studying these galaxies often describe them as time capsules, fossils of an earlier universe. Because they have experienced so few interactions, their structures and compositions preserve the conditions of their birth. Many of them have low metallicity, meaning their stars contain fewer heavy elements like iron and carbon. Those elements are forged in the hearts of stars and spread when stars die, especially in galaxies that merge and share material. In voids without frequent mergers, enrichment happens slowly. The result is a cosmic garden with poorer soil, where stars grow in smaller numbers, and planets with complex chemistry are rarer. It's tempting to think of that as a disadvantage, but it may also be a gift. In dense regions, galaxies evolve quickly and sometimes violently. In voids, they have time, immense spans of it, to develop undisturbed. If there are civilizations in such places, they might live under quieter skies, free from the blinding lights of crowded clusters. Their nights would be darker, their galaxies fainter, but their ages of peace might stretch far longer than our own. Astronomers have found that galaxies and voids often retain large reservoirs of neutral hydrogen gas, the basic fuel for new stars. This gas emits a faint radio whisper that can be detected by sensitive instruments. Mapping that signal shows long, thread-like structures connecting galaxies, ghostly veins of hydrogen threading through the emptiness. They are reminders that even here, matter is not gone. It is merely sparse, waiting. In some ways, these hydrogen threads echo the structure of the larger universe, the same cosmic web, just more delicate. They feed their galaxies slowly, allowing for steady, patient star formation. Over billions of years, such galaxies can evolve into graceful, open spirals with thin arms and luminous centers. Others remain diffuse and fragile, as if reluctant to commit to the act of shining too brightly. Each follows its own path, guided more by time than by tension. Studying these galaxies gives astronomers a new perspective on cosmic evolution. They show what happens when gravity and chaos step back and patience takes the lead. In the crowded cosmic cities, galaxies change through collision and fire. In the quiet countryside of the universe, the voids, they change through reflection, drifting through aeons without hurry. The difference between the two is like the difference between a storm and a gentle breeze. Both move the air, but the breeze shapes it with tenderness. The KBC Supervoid, with its lower density and weaker gravitational tides, is home to many of these serene galaxies. Their light reaches us across millions of years, untouched by the confusion of busy clusters. It tells a story of endurance, of systems that chose by circumstance the long road of solitude. Some may never join larger clusters at all. They will fade with the universe's expansion, each becoming an isolated island of stars, still orbiting their unseen dark halos long after the cosmic web stretches beyond recognition. When we look at them through our telescopes, we're not just studying distant objects. We're witnessing the slow art of survival. These galaxies have found a way to exist with less matter, less gravity, fewer neighbours, and somehow that very scarcity has made them pure. They show us that life, in any form, doesn't always need abundance. Sometimes it just needs quiet. If the crowded clusters are the universe's loud conversations, then the void galaxies are its whispered thoughts, fragments of light drifting through stillness, carrying within them the memory of what creation sounds like when nothing interrupts it. They are proof that even in the vast silence, the cosmos continues to write, patiently, line by line. Every star, every planet, every breath of air you take is made from the ashes of earlier stars. Hydrogen and helium were born in the first few minutes after the Big Bang, but everything heavier, carbon, oxygen, iron, gold, had to be forged later inside stars that lived, burned, and died. When those stars exploded, they seeded the universe with dust and metals, sprinkling the ingredients of life into the cosmic sea. Astronomers call this gradual enrichment metallicity, though the word metal here means more than just shiny elements. It means everything solid, everything complex, the stardust from which worlds and people are made. In crowded regions of the universe, galaxies enrich quickly. They merge and collide, sharing their gases and dust, triggering wave after wave of star formation. Each generation of stars adds more heavy elements to the interstellar medium, and over time those galaxies turn redder, older, richer. But in the emptiness of the voids, this process unfolds at a far gentler pace. There are fewer collisions, fewer supernovae, fewer opportunities to stir the cosmic soup. The galaxies that live here are chemists working with half-empty shelves. Patient, meticulous, never in a rush. When astronomers measure the metallicity of void galaxies, they find it is lower than that of similar galaxies in denser regions, but not as low as one might expect. Something is feeding them, replenishing their ingredients slowly but steadily. The likely answer lies in the faint ghost-like filaments of gas that weave through the voids, tendrils of cold hydrogen reaching across millions of light years, almost invisible except in radio waves. These filaments act like arteries, carrying fresh material into isolated galaxies, fueling star formation even in the loneliest corners of the universe. They also allow some of the processed gas to escape, creating a quiet cycle of inflow and outflow, a cosmic form of breathing. You might picture it as a vast, translucent web of veins, pulsing gently with the slow heartbeat of creation. Along these veins, galaxies sip from the universe's reserves, transforming hydrogen into light, releasing traces of carbon and oxygen, and exhaling them back into the intergalactic dark. It is recycling at a scale so immense that the concept almost slips beyond comprehension, yet the pattern is familiar. Every forest breathes in carbon dioxide and exhales oxygen. Every ocean exchanges heat and moisture with the sky. Every star, every void galaxy is part of that same rhythm of renewal. The gas that flows through these filaments is cold by cosmic standards, only a few thousand degrees above absolute zero. To human senses, that would feel unimaginably hot, but in astrophysical terms it's chilled enough to condense and form new stars. When this hydrogen gathers into clouds, gravity begins its patient work. The cloud collapses, its atoms squeeze together, and the first fusion reactions ignite. A new star is born, glowing faintly blue or white against the soft darkness. In a typical void galaxy, these births happen sporadically, not in the massive bursts we see elsewhere. It's a slow, deliberate process. A few new stars each century, lighting up the emptiness one spark at a time. Over billions of years, these gentle cycles add a small but noticeable amount of heavy elements to the galaxy. The stars that form later have more complex chemistry than their ancestors. Their planets, if they form at all, may have enough carbon and oxygen to support atmospheres, perhaps even oceans. Still, compared to the crowded regions of the cosmic web, void galaxies remain poor in metals. Their stars are younger, their planets rarer, their skies dimmer. They live in what might be called a cosmic wilderness, far from the bustling metropolises of galactic clusters. To many astronomers, these galaxies are natural laboratories for studying how the universe works when nothing interferes. Without the chaos of frequent mergers, they reveal the underlying simplicity of cosmic evolution. How does a galaxy grow when left to itself? How does star formation proceed when time stretches unbroken for billions of years? The answers lie in these quiet, isolated systems, shining with the light of patience. The chemistry of isolation also tells us something about the larger cosmic balance. Heavy elements are not just decorations, they are regulators. They help cool gas clouds so that stars can form. They shape how light is absorbed and scattered. They determine what kind of planets can emerge and what atmospheres they might hold. When metallicity is low, the universe is quieter. Fewer supernovae, fewer flashes of brilliance, more steady glows. In this sense, the void galaxies are the universe's slow burners, sustaining a gentle flame that never quite goes out. If you could stand on a planet inside such a galaxy, assuming one existed, the night sky would look different from ours. The Milky Way, with its glowing river of light, would be replaced by a thinner, fainter arch. The nearest neighbouring galaxies might appear as tiny smudges, hardly brighter than the faintest stars. Yet the air of that world, the water in its seas, the minerals beneath its surface, would still come from the same universal chemistry. the slow alchemy of hydrogen into heavier things. Even in isolation, the recipe of creation doesn't change, only the tempo does. Sometimes astronomers speak of these regions as cosmic deserts, but perhaps that metaphor misses something. Deserts on Earth are not dead. They are places of resilience, where life adapts to scarcity and endures with grace. In the same way, the galaxies of the void are not barren. They are resilient. Their stars form against the odds, their gas filaments endure across billions of light years, and their faint glow continues long after brighter galaxies burn through their fuel. They are monuments to longevity, to persistence, to the quiet power of time. The chemistry within these galaxies also has a subtle relationship with the great cosmic forces that shape everything. In dense regions, gravity dominates. In voids, gravity retreats, and dark energy, the mysterious pressure that accelerates expansion, becomes more visible. Here, in these underdense spaces, the gentle stretching of the cosmos itself influences how gas flows, how galaxies evolve, and how light travels. The chemistry of isolation becomes a mirror for the physics of the universe's future. Slow expansion, cooling, and a long twilight of fading creation. Even in emptiness, the universe finds ways to connect its parts. Hydrogen filaments bridge the distances, light carries the memory of where it has been, and gravity's faint tug keeps the dance in motion. You could say that in the void, creation speaks softly but endlessly. The galaxies there are not mistakes or leftovers. They are the proof that the universe never stops trying to make something new, even in its quietest places. And perhaps that is the lesson of the void, that scarcity is not the end of beauty. The galaxies that grew here, enriched atom by atom, teach us that patience itself can be a form of abundance. In their dim, enduring glow, we can see the universe as it truly is, a vast and thoughtful chemist, still mixing its elements in silence. If gravity is the universe's embrace, then dark energy is its sigh, a quiet pressure that makes space itself expand. We don't yet know what dark energy truly is. It has no colour, no texture, no direct signal we can detect, and yet its influence is everywhere, woven through the cosmos like an invisible wind. It pushes galaxies apart, drives the acceleration of expansion, and determines the ultimate fate of everything. In crowded regions of the universe, the pull of gravity competes with it. But in the emptiness of cosmic voids, where there is little to pull back, dark energy's influence becomes beautifully clear. Inside the KBC Supervoid, this gentle pressure dominates. With less matter to counterbalance it, the expansion of space proceeds more freely. Galaxies drift apart faster, light stretches more easily, and the geometry of space takes on a subtle outward curve. It's as if the universe itself loosens its shoulders here, relaxing after the dense tug-of-war of clusters and filaments. For astronomers, voids like this become natural observatories for studying dark energy. Wide, uncluttered rooms where the quiet hum of cosmic acceleration can be heard without interference. When we think of expansion, it's easy to imagine something explosive, galaxies flying away from one another like shrapnel. But the true picture is far more graceful. Space doesn't explode, it swells. Every patch of emptiness gently stretches, carrying galaxies with it like dots on a rising loaf of bread. In voids, where there's little mass to slow that stretching, the process feels almost serene, a steady, unstoppable drift rather than a violent burst. The rate of expansion here reflects the balance between gravity's grip and dark energy's push, and in these hollow spaces, the push wins. Astronomers study this balance by measuring how voids evolve over time, how their sizes, shapes, and depths change as the universe ages. The idea is simple. If dark energy is constant, like a built-in pressure of space itself, then voids should expand in a predictable way. But if dark energy changes with time, growing stronger or weaker, That change will be written in the shapes of the voids. A slightly faster expansion would make them puff out more quickly. A slower one would let gravity's subtle pull rein them in. By comparing observations across different eras of cosmic history, scientists can test which story is true. To detect such faint effects, astronomers rely on enormous surveys that map millions of galaxies. The Sloan Digital Sky Survey, the Dark Energy Survey, and the upcoming Euclid and Rubin observatories each aim to capture not just where galaxies are, but how they cluster, how they drift, and how the empty spaces between them breathe. In this way, voids become cosmic barometers, instruments that measure the pressure of the universe itself. The more precisely we can chart their shapes, the more accurately we can sense the weightless hand of dark energy at work. The beauty of studying dark energy through voids is that they remove much of the cosmic clutter. In dense regions, matter complicates everything. Gravity pulls in multiple directions, stars burst and fade, and the motions of galaxies intertwine like tangled strings. But in the emptiness, simplicity emerges. The expansion there follows the clean mathematics of space-time itself. It's the closest we can get to watching the universe act on its own terms, unburdened by the noise of creation. You might imagine a void as a vast bubble suspended within the cosmic web. It's not empty, but it's smooth, with a density only a fraction of the cosmic average. At its centre, dark energy's influence is pure, a quiet push in every direction. If you could mark the positions of galaxies along its boundary and wait a few billion years, you'd see that boundary drift outward, like the skin of a soap bubble expanding in slow motion. The galaxies inside would move gently apart, their separation increasing not because they're flying away, but because the space between them is stretching. It's tempting to ask, what exactly is doing the pushing? Some theories describe dark energy as the energy of the vacuum itself, a property of space that can't be removed. Others imagine it as a dynamic field, something that can change over time, like a tide slowly shifting the shape of the cosmos. Whatever it is, its effects are clear. Without dark energy, the universe's expansion would have slowed and eventually reversed, collapsing into itself in what physicists once called the Big Crunch. With dark energy, the opposite happens. Expansion accelerates, carrying galaxies farther and farther apart until even light cannot bridge the growing gulf. Inside a void like the KBC region, we get a small preview of that future. The dominance of dark energy here makes the local expansion a bit stronger than elsewhere, a gentle acceleration visible in the motions of galaxies and the stretching of light. It's as if we live in a microcosm of the universe's destiny, a small-scale rehearsal for the great widening to come. And yet, for all its vastness, dark energy feels oddly intimate. It connects directly to the way we experience reality. Every time you look up at the night sky, the space between you and those stars has grown slightly larger since their light began its journey. Every photograph of a distant galaxy is also a photograph of change, the space between us lengthening as the years pass. That quiet expansion is the signature of dark energy, a reminder that even stillness is movement when seen from a cosmic perspective. To live inside a void surrounded by the soft pressure of this invisible force is to live in one of the universe's purest laboratories. Here, in the absence of distractions, we can glimpse the underlying rhythm of space-time. The equations that describe it may be complex, but their essence is simple. Gravity gathers, dark energy disperses. One pulls, the other releases. And somewhere between the two, balance emerges, not static, but harmonious. The KBC Supervoid gives that harmony a visible form. Its gently curved walls, its sparse galaxies, its faster than average expansion, all of them are signs of the same phenomenon that drives the entire cosmos. In studying it, we're not just measuring a region of space, we are measuring the pulse of the universe itself. Sometimes scientists describe this as a kind of cosmic experiment we didn't plan but were fortunate enough to inherit. We didn't choose to live inside a void, but its emptiness gives us a clearer view of the most elusive energy in existence. It reminds us that even nothingness has something to say, if we're patient enough to listen. And perhaps, in a quiet way, that's what dark energy is trying to teach us. That expansion need not be loud or sudden, that the universe can grow without explosion, and that even in the softest silence there is motion beyond measure, a bubble of space, expanding not by force, but by quiet insistence, a universe breathing out. Since the dawn of modern astronomy, there has been a quiet assumption guiding all our maps and measurements, that the universe is fair. It's called the Cosmological Principle, and it rests on a simple, comforting idea that no place is truly special. If you could drift far enough in any direction, you'd see roughly the same scenery, the same balance of light and dark, the same ratio of galaxies to space, the same cosmic rules at play. We are not at the centre of anything. We're not exceptional. The cosmos, in its enormity, treats every location equally. This idea has served us well for a century. It allowed scientists to construct models of the universe that are elegant, symmetrical, and manageable. It gave us confidence that by studying one corner of the cosmos we could understand them all. But the discovery of the KBC Supervoid, our vast underdense cosmic neighbourhood, has gently unsettled that picture. Because if we really do live inside a bubble of unusual emptiness, then the universe might not be as even-handed as we hoped. It might still be fair in principle, but locally we are sitting in a small exception, a quiet cul-de-sac in an otherwise busy town. The question isn't whether the cosmological principle is wrong, but whether it's too simple. The universe could still be homogeneous and isotropic on the larger scales, smooth when viewed from far enough away, while containing structures like voids and filaments that make it patchy up close. The trick is knowing where the boundary lies. How large must the cosmos be before its irregularities even out? And if our region happens to be atypical, how much does that colour our interpretation of everything else? Astronomers wrestle with this question carefully. Some argue that the KBC region is just a statistical fluctuation, a rare but not impossible coincidence in a universe built on randomness. After all, even in a perfectly fair system, coincidences happen. But others see it as a clue that our models of cosmic uniformity might need refining. The assumption that everything averages out may not hold as neatly as we once thought. And if it doesn't, then our measurements of distance, of expansion, of time itself may carry a local bias we've yet to fully account for. There are two ways to reconcile this, and each one carries its own philosophical weight. The first is to accept that we occupy a rare position. In this view, our location is not privileged in a spiritual sense, just unusual in a statistical one, like being born in a small, quiet town in a vast empire of cities. The universe is still fair, we just happen to live in one of its quieter provinces. It's an accident, not a message. This explanation keeps the laws of physics untouched, but asks us to accept a little geographical humility. We are not the cosmic average. The second path is more daring. It suggests that maybe the rules themselves need a small adjustment, that gravity, dark energy, or the initial conditions of the universe might vary slightly from place to place, or evolve in ways we haven't captured. In this view, the KBC Supervoid is not an anomaly but a clue. Perhaps it hints that the cosmic principle of sameness is not absolute but approximate, a simplification that hides deeper complexity. Maybe the universe is even more creative than our equations allow, filling its vastness not with identical patterns, but with subtle variations like brushstrokes in an endless painting. Whichever view proves true, the discussion changes how we think about our place in the cosmos. For centuries, each scientific revolution has nudged us farther from the centre, from Earth to Sun, from galaxy to cluster, from cluster to nowhere in particular. The Cosmological Principle was the culmination of that trend, a declaration that we are ordinary, statistically unremarkable, just one observer among billions in a universe without bias. Now, the possibility that we live inside a giant cosmic void complicates that humility. It doesn't make us special in a romantic sense, but it does make our neighbourhood distinct. We are witnesses from an unusually quiet vantage point. Some astronomers find this disquieting, others poetic. It means that the universe, even when it obeys the same physical laws everywhere, still allows room for individuality, for places that are calm while others are crowded, for regions of darkness beside seas of light. The KBC Void might be one such region, a cosmic version of a tranquil bay along a stormy coast. The sea follows the same tides everywhere, but not every shore feels the same waves. If you could stand outside the universe and look in, you might see it as a grand mosaic, clusters and superclusters glowing like jewels, separated by great gaps of shadow. On average, it's balanced and beautiful. But zoom in on one part, our part, and you'd find a stretch of relative emptiness. The symmetry remains, but it's not perfect. And maybe that imperfection is part of the design. The universe, like a painting or a song, gains depth from its variations. Philosophically, this challenges our sense of cosmic fairness. We've long believed in the Copernican principle, the idea that we don't occupy a special position, but perhaps there's another way to read it. Maybe our non-specialness doesn't mean sameness. Maybe it means that every place, even an empty one, has its own role in the cosmic composition. The dense clusters blazing with galaxies play one note. The voids, whispering with faint blue spirals, play another. Together they create harmony, a universe that is balanced not by uniformity, but by contrast. When scientists talk about the cosmological principle being on trial, it's not because they wish to overthrow it, but because they're testing its limits. Like any principle in science, it's a starting point, not a dogma. The discovery of the KBC Void invites us to refine that starting point, to see homogeneity not as absolute equality, but as gentle consistency. The universe doesn't need to be identical in every direction for its laws to hold. It only needs to be coherent enough that those laws make sense wherever we look, and in a way that realization brings us back to humility. The cosmos isn't designed around us, nor does it have to be perfectly even for us to understand it. We're simply lucky to observe from a place that offers a clear view, a quiet balcony overlooking the greater storm. Our corner of the universe, with its slightly faster expansion and its scarcity of matter, is one of infinite perspectives within the same unfolding story. So perhaps the universe is even after all, not in the symmetry of its shapes, but in the equality of its beauty. Some regions shine with the brilliance of crowded stars, others, like ours, glow softly with emptiness. Each is part of the same cosmic truth, expressed through different moods. When we gaze into the dark, we're not looking at a violation of fairness. We're looking at the other half of it, the silence that completes the sound. Time, c'est one en efforts. Science has always lived in the space between certainty and curiosity. Every time we think we have measured the universe precisely, a new question slips quietly through the gaps. The discovery that our local expansion rate seems higher than the cosmic average, the Hubble tension, is one of those questions. The KBC Supervoid may be part of the answer, but it's not the only story scientists are considering. There are other possibilities, each like a different interpretation of a familiar melody. Some are simple tuning adjustments, others propose that the instrument itself plays by new rules. The first possibility is that the tension is not truly cosmic but local, a result of how we measure distances and the speed of expansion. Measuring the universe is an art built on ladders. We start with nearby stars, then climb upward using more distant objects, each step calibrated by the one below. This is called the cosmic distance ladder. It sounds straightforward, but every rung introduces uncertainty. The brightness of certain stars, known as Cepheids, might vary slightly depending on their environment. Supernovae, used as cosmic beacons, might not be perfectly consistent from one galaxy to another. Even the dust that floats between stars can alter how bright these lights appear, and a small bias here or there can ripple upward until it affects our final measurements of expansion. If the nearby measurements are subtly overstated, if our local rungs are just a little too long, then the apparent Hubble constant would naturally come out higher. In that case, the void isn't solely responsible for the difference, it merely amplifies it. To correct this, astronomers are re-examining each link in the distance chain, comparing independent methods. Some use the light from red giant stars, others rely on gravitational lensing delays, where light from distant quasars bends around massive galaxies, creating multiple images that flicker at slightly different times. Each method provides a check, a way to make sure that what we call distance in the universe is not an illusion created by the way we see. The second explanation lies deeper, in the heart of physics itself. Perhaps the equations that describe gravity, Einstein's general relativity, are nearly right, but not quite complete. Some scientists propose modifications known collectively as Mund-like theories, short for modified Newtonian dynamics. These ideas suggest that gravity behaves differently at extremely low accelerations, the kind found between galaxies and across cosmic voids. If true, the universe's expansion might not follow the simple balance we expect between matter and dark energy. It could speed up or slow down depending on the subtle curvature of space and the distribution of invisible mass. Other theories take an even bolder approach. They suggest that dark energy itself may not be constant. Instead of being a fixed property of space, it could be a field that evolves with time, a cosmic tide that waxes and wanes. In such models, the universe's expansion history would depend on when and where you measure it. Our local region, sitting inside the KBC Supervoid, might feel a slightly stronger pull from this dynamic dark energy than the universe at large. In that case, the Hubble tension wouldn't be an error. It would be a clue that dark energy is alive, changing as the cosmos matures. Then there are explanations that reach back to the earliest moments after the Big Bang. The seeds of structure, the initial ripples that became galaxies and voids, might not have been perfectly random. A small asymmetry in those primordial fluctuations could have left us inside a region that expands a little faster than average. It would be as if the cosmic dice rolled in our favour, placing us in one of the rare patches where space stretched slightly more than elsewhere. The universe would still obey the same rules everywhere, but the initial conditions would have given our neighbourhood a head start. Each of these scenarios fits the data in its own way, but none has yet closed the case. And that's the beauty of science. It doesn't rush to verdicts. It lets ideas compete in the open air of observation. Over the next decade, a new generation of instruments will step into this debate. The dark energy spectroscopic instrument DESI is already charting the positions of tens of millions of galaxies, measuring how their light shifts with distance. The Vera Rubin Observatory will soon begin scanning the entire sky every few nights, creating a moving picture of cosmic change. The Euclid Space Telescope, launched by the European Space Agency, will map the subtle bending of light caused by gravity across billions of light years. Each of these missions will act as a kind of cross-examination, independent witnesses testifying to the universe's true behaviour. It's possible that when all the evidence is in, the tension will dissolve into clarity. Perhaps a few small corrections, a better calibration here, a refined measurement there, will bring the local and global expansion rates into harmony. But it's equally possible that we'll find something new, something that forces us to revise our cosmic score. And if that happens, it won't be the first time the universe has surprised us. When Einstein introduced the idea of a cosmological constant, the forerunner of dark energy, he called it a mistake after expansion was discovered. Decades later, it returned, vindicated by new observations. The universe, it seems, has a quiet sense of irony. Every time we declare our understanding complete, it reminds us to keep listening. The KBC Supervoid, the Hubble tension, the mismatched measurements, these are not contradictions but invitations. Each one whispers that reality might still have verses we haven't read. In moments like these, it helps to remember what science truly is. It's not a book of answers but a conversation with the unknown. Theories rise and fall, but curiosity endures. The same patience that governs star formation in void galaxies also guides our search for understanding. We test, we measure, we wait. We allow uncertainty to speak. And maybe, in that waiting, there's a lesson. The universe doesn't reveal its secrets in loud announcements. It does so in soft inconsistencies, in gentle disagreements between numbers. The Hubble tension, the KBC void, the possible shifts in dark energy, all of them are examples of the cosmos nudging us to look closer. They remind us that precision is not the end of wonder. Even when our equations almost fit, the universe reserves the right to surprise us. So the next time you hear scientists debating the value of the Hubble constant or arguing over whether dark energy is constant or alive, know that it's not just a technical dispute. It's a love letter to curiosity, a sign that we are still listening to the universe's quietest notes. The answer, when it comes, may not change the stars, but it will change how we hear their silence. When we speak about the age of the universe, we often do so with a tone of certainty, about 13.8 billion years. It sounds so precise, as if we have looked at a cosmic clock and read the time directly. But in truth, this number is the product of delicate inferences and deep patience. We measure it by observing the faintest light, by watching the slow motion of galaxies, and by tracing the whisper of ancient starlight back to its origin. Every method, every assumption must fit together perfectly. And yet, in recent years, a small paradox has begun to whisper through that harmony. If the universe is expanding faster nearby than it does on average, does that mean it could also seem younger from our perspective? It's a question that has quietly unsettled cosmologists. If we take the higher local expansion rate, the one measured within our cosmic neighbourhood, and use it to estimate the age of the universe, we get a number around 12.5 billion years. But some of the oldest stars we can observe, like those in the ancient globular clusters orbiting our galaxy, appear to be nearly as old, perhaps 12 to 13 billion years themselves. A faster expansion implies a younger universe, but those stars seem unwilling to cooperate with that story. It's as if we had aged more slowly than the cosmos around us, or perhaps that our local corner of space ticks to a slightly different tempo. To understand this gently, imagine the universe as a great loaf of rising dough. In the denser regions, gravity slows the rise. In the emptier regions, like our KBC Supervoid, the dough stretches faster. From inside such a region, everything would seem to move outward more quickly, as if the universe were expanding faster than average. But that doesn't mean the whole loaf baked more quickly. It only means our local patch rose a little higher, a local variation in a grand, uniform process. The cosmic age itself doesn't change, only our view of the clock does. Astronomers test these ideas using several kinds of stellar chronometers. Globular clusters, dense swarms of ancient stars, act as cosmic fossils. By measuring how their brightness and colour have evolved, scientists can estimate how long their stars have been shining. The results place their ages between 12 and 13 billion years, suggesting they formed soon after the first galaxies took shape. White dwarfs, the faint cinders left behind when smaller stars die, offer another kind of clock. As they cool slowly over time, their temperatures record the passage of billions of years. The coolest among them in our galaxy also point to ages around 12 to 13 billion years. These independent timepieces carved into the night sky agree with the slower, older age given by the cosmic microwave background. The 13.8 billion years that comes from studying the universe as a whole. So, where does the paradox truly lie? It lies in perspective. When we measure the expansion rate close to home, inside our local void, we are hearing the universe's tempo played slightly faster, a regional variation that makes the cosmos appear younger than it is. Beyond the edges of the KBC Supervoid, where matter density returns to normal, the pace slows back to the global average. If we could step outside our cosmic hollow and look back, we'd see our region as one that's simply breathing a little more quickly than the rest. The stars themselves don't contradict the cosmic age, they remind us to adjust our view. This reconciliation has a quiet beauty to it. It tells us that the universe is consistent after all, that even when local measurements seem to disagree with distant ones, both can be true within their own context. Time, like space, bends gently with the structure of the cosmos. In emptier regions where gravity's pull is weaker, the flow of time and the rate of expansion both stretch a little. It's as if the universe lets its quieter corners move at their own rhythm, yet still keeps them in harmony with the larger symphony. For astronomers, this realization is both relief and revelation. It means we don't need to rewrite the story of cosmic time, we just need to read it more carefully. The apparent youth of our neighborhood isn't a flaw, it's a feature of perspective, a subtle echo of the geometry of emptiness. Our local void makes the clock seem to tick faster, but the true cosmic clock, the one that began with the Big Bang, still keeps steady time. And what a clock it is. Over those 13 or so billion years, hydrogen clouds have turned into galaxies, galaxies into clusters, and stars into everything we know. Life has emerged, thought has awakened, and now, from this small blue planet, we are listening to the faint rhythm of the universe's expansion and trying to trace it backward to its first heartbeat. The paradox of time's age, instead of being a source of confusion, becomes a reminder of how astonishingly consistent the cosmos is. Even the smallest local peculiarities, a faster expansion here, a slower one there, fit within a grand order that remains unbroken. There's a gentle poetry in this, the idea that the universe allows small imperfections that make it more beautiful. If every region expanded at exactly the same rate, if every measurement fit too neatly, the cosmos would feel static, almost mechanical. But the slight variations, the whispers of tension and difference, give it life. They show us that even the laws of physics permit individuality, that the universe is not a rigid machine but a vast breathing organism, each part responding to its environment while remaining part of the whole. You could say that the KBC Supervoid has given us more than a scientific puzzle. It has given us a mirror. It shows how easily perspective can shift what we think we know. Just as standing in a valley makes mountains look taller, living in an underdense region makes the universe appear younger and faster. Yet neither perception is wrong. They are two sides of the same truth. The truth that time and space are not absolute but interwoven, shaped by the fabric of existence itself. When you gaze up at the stars tonight, you're looking at moments separated by billions of years, all arriving together in your eyes. Some of that light left its source before the Earth existed. Some began its journey before our galaxy finished forming. And yet to you, it feels like one sky, one present moment. That illusion of simultaneity, that merging of past and now, is the universe's most graceful trick. It's the same trick that lets us measure its age, and the same one that lets a local void seem young while the cosmos remains ancient. So perhaps time, like the universe, is both constant and personal. The stars measure it in billions of years, we measure it in breaths. Inside our cosmic hollow, both scales meet, the human and the infinite, reminding us that perspective is not a limitation, but a way of belonging. The universe doesn't hide its age from us, it simply invites us to see it from where we stand. Sometimes youth is only an illusion of where we are, not what we are part of, and that, in its quiet way, may be the most reassuring truth of all. The cosmos is not younger or older here. It's just being itself, patiently unfolding as it always has. Try to imagine the far future, not in centuries or millennia, but in tens of billions of years. By then, the night sky will look very different. The stars we know will have drifted away, their light stretched thin by the universe's relentless expansion. The Milky Way will have long merged with its neighbour, Andromeda, forming a single, massive island of stars that astronomers sometimes call Milkdromeda. Beyond it, there will be almost nothing left to see. The rest of the universe, the countless galaxies that fill today's telescopes, will have slipped quietly beyond our horizon, carried away faster than light by the acceleration of space itself. The sky of the future will forget its own story. The same gentle pressure that now drives the KBC Supervoid's expansion will one day push the entire cosmos into isolation. Dark energy, that quiet, steady force of expansion, will not stop. It will continue to stretch the fabric of space until the distances between galaxies grow so vast that even light can no longer cross them. Astronomers call this cosmic isolation, though the phrase doesn't quite capture the poignancy of it. In time, every observer in every galaxy will become blind to the universe beyond their local cluster. The grand cosmic web we see today will dissolve, its filaments pulled apart until they fade into invisibility. Inside a void like the one we inhabit, that future will come even sooner. With fewer galaxies to begin with, the night will grow darker faster. Already, our sky is sparser than that of denser regions, where clusters crowd together like glowing cities. In our quiet cosmic countryside, the lights are fewer, and the spaces between them are wider. Fast forward tens of billions of years, and the galaxies at the edge of the KBC Supervoid will vanish one by one, their light stretched beyond detectability. Eventually, even the faint afterglow of the Big Bang, the cosmic microwave background, will fade below the threshold of observation. The universe will still be full of energy, but it will be energy too diluted to see. It's strange to think that there will come a time when the evidence of the universe's own birth will be gone. Future astronomers, if any remain, will look into the sky and see only the stars of their merged home galaxy. They might conclude that theirs is the entire universe, a single island adrift in eternal darkness. The expansion, the Big Bang, the vast network of galaxies, all of it will be invisible to them. They will live in what physicists sometimes call a cosmic dark age, not because light will disappear entirely, but because the light of the larger cosmos will no longer reach them. From our vantage point, this feels almost melancholic. We live in a uniquely privileged time, a moment when the universe is still transparent, when its early light still lingers, and when galaxies are near enough to study. We can measure the faint afterglow of creation, trace the filaments of the cosmic web, and glimpse the structure of voids like our own. 100 billion years from now, those same measurements will be impossible. The evidence will have drifted beyond reach, erased not by destruction but by distance. Yet there's a kind of beauty in this too. The universe is not vanishing, it's simply evolving. Its story isn't ending, it's changing chapters. What follows the era of light and discovery is an era of memory and reflection. The galaxies that remain will keep shining for trillions of years, their stars burning slowly as they circle the quiet core of what used to be many. Within that long twilight, there may still be worlds orbiting stable suns, and perhaps beings who look up and wonder, as we do now, what lies beyond their horizon. They may never know, but they will still feel the pull of curiosity, the ancient instinct that seems built into the very fabric of awareness. In a way, our current view of the universe, this wide, open panorama of galaxies stretching for billions of light years, is temporary, a fleeting window between opacity and silence. For most of cosmic history, the universe was too dense and hot for light to travel freely. And in the far future, it will be too stretched and faint for light to connect distant places. We live in the middle, the luminous interlude. The cosmos has opened its eyes just long enough for us to see it, and then, slowly, they will close again. For scientists, this understanding carries both awe and urgency. It means that everything we observe, every map we make, every photon we catch from a distant star, is part of a vanishing record. The information is finite, and so is the time we have to gather it. The KBC Supervoid, once a curiosity, becomes part of that record, a rare glimpse of structure before the universe grows too quiet to reveal its shape. The work of cosmology, then, is not just to measure but to preserve. We are the archivists of the universe's visible age, tasked with recording its grandeur before the light fades. If you imagine time as a great ocean wave, we're standing near its crest, looking out across the shining face just before it begins to fall away. The wave will keep moving, and so will we, carried along by the same laws that guide every star and atom. There's no tragedy in that, only continuity. The universe doesn't mourn its changes, it simply becomes. Still, there's something profoundly human about our desire to remember, to fix the fleeting, to hold on to what cannot be held. Maybe that's why we build observatories, launch telescopes, and write theories that stretch across epochs. It's our way of leaving messages for the future, even for a future that might never hear them. If someday, in that distant age of isolation, a civilization looks inward rather than outward, perhaps they will find those messages, the data, the equations, the quiet poems written in starlight, and realize that once the universe was known in all its vastness. When that time comes, when the last galaxies beyond the local group slip from view, the cosmos will not feel empty to those who inhabit it. Their sky will still shine, and within that light will be all the elements of life and history. The universe, after all, is not only what it reveals, it is also what it sustains. Even in its isolation, it will continue to host stars, planets, and the quiet persistence of existence itself. So, as we look ahead to that distant future, we can do so without sadness. The coming darkness is not an ending, but a deep rest. The universe taking a breath after its long expansion, letting its light fade into peace. And for now, while we can still see across billions of light years, we are witnessing a miracle of timing, the brief, shining moment when the cosmos allows its own reflection to be seen. If the universe could dream, perhaps it would dream of silence. After the bright turmoil of its youth, the bursting stars, the colliding galaxies, the roaring tides of creation, there comes a time when everything slows. The light softens, the distances widen, and the great web of galaxies stretches thin. Yet even as the cosmos grows quiet, it never becomes empty. It simply enters another phase, a slower rhythm, a gentler breath. Inside the voids, like the one we call home, this calm has already begun. Life, as we understand it, is deeply tied to the chemistry of stars. It depends on heavy elements: carbon for the backbone of molecules, oxygen for water, iron for the blood of worlds. These elements are built in the hearts of massive stars and scattered by their deaths. In dense regions where galaxies collide often, that enrichment happens quickly. New generations of stars inherit the ashes of their predecessors and give rise to complex planets, rich atmospheres, and, eventually perhaps, the spark of awareness. In the underdense regions, the story unfolds differently. Fewer collisions mean fewer explosions, fewer metals, and a slower chemical evolution. The galaxies of the void, rich in hydrogen but poor in heavier ingredients, offer a different kind of environment, quieter, simpler, and more patient. If life arises here, it does so under dimmer skies, on worlds orbiting smaller stars, with long stretches of calm between cosmic events. The dangers are fewer supernovae, fewer bursts of radiation, fewer gravitational disruptions. But so are the resources. Life in these places would grow slowly, like lichen on stone, shaped by scarcity rather than abundance. Some scientists have wondered whether the voids might actually be the safest havens in the cosmos. In clusters, where galaxies crowd together, gravitational chaos and energetic explosions can sterilize vast regions. But in the emptiness, a planet can circle its star for billions of years without disturbance. Stability replaces excitement. There's time for biology to experiment, to fail, and to begin again. A civilization born in such a place might learn the art of endurance early, patient, reflective, and quietly attuned to the rhythm of change. They would live under skies where each star is a solitary companion, far from the glittering crowds. Their telescopes, if they had them, would see almost nothing beyond their own galaxy. The universe, to them, would appear small, intimate, and infinite all at once. It's humbling to imagine that possibility, that life might persist not in the centres of cosmic activity, but at its edges, in the thin air of existence. It suggests that the conditions for thought and wonder do not require a grand stage. They only need time and a little light. Perhaps life is less like a firework and more like a candle, glowing longest where the air is still. The relationship between life and the cosmos is one of rhythm, not privilege. The same physical laws that stretch galaxies apart also allow atoms to assemble into living beings. The same dark energy that will one day silence the universe also gives it the smoothness and stability necessary for stars and planets to form. We are not guests in a hostile universe. We are expressions of its patience. Our consciousness, fragile though it is, arises naturally from the long interplay between gravity's pull and space's quiet expansion. In that sense, awareness is not an accident. It's a continuation, the universe learning, through us, to notice itself. When we look outward from the KBC Supervoid, we are looking through one of the calmest parts of the cosmic ocean. The galaxies around us drift apart, but they do so in silence, without storms or collisions. The light that reaches us comes undisturbed, like messages travelling across still water. From here, we can observe the universe in its purest form, a vast equilibrium of motion and rest, and in that stillness, perhaps, lies meaning. The question of meaning, of course, is one that science cannot measure, but it can inspire. It can show us that the story of the universe is not one of decay, but of transformation. Energy does not vanish, it changes form. Light may fade, but it becomes warmth, gravity, and memory. Even when the last star flickers out trillions of years from now, its atoms will continue to drift, still tracing the geometry of what once was. And if there is consciousness somewhere, it may look upon that quiet and feel not despair, but peace. In that far future, when the skies grow dark and only local galaxies remain visible, the cosmos will still carry the echo of everything that came before. The voids will remain as soft corridors through which time flows freely. Maybe within one of those galaxies another form of life will rise, different from ours, built for endurance rather than discovery. They might never know the vastness that once was, but they will still feel it in their bones, in the laws that shape their world. The physics of expansion will be written into their history, just as it is written into ours. It's easy to imagine that we are living at the end of something, the fading edge of cosmic revelation. But perhaps we're simply in the middle, part of an endless sequence of awareness blooming, fading, and blooming again. The universe does not hurry. It does not worry about beginnings or ends. It expands. It cools. It breathes. Each civilization that looks up at its stars becomes a temporary voice in that long breathing, a note in the quiet music of existence. The KBC Supervoid, for all its emptiness, is a reminder of this. It teaches us that absence is not the opposite of life, but a condition for it. Without space to expand, without the silence between galaxies, there would be no place for stars to form or for minds to wonder. Emptiness, in its strange generosity, makes everything possible. So, as you drift into rest tonight, remember this. We live inside a quiet bubble in a vast and endless sea. The stars around us may seem distant, but their light is old and kind, travelling across billions of years to find you here, now, listening. You are part of that light, a momentary flicker of the universe's long awareness. The cosmos breathes, and you breathe with it. The universe expands, and so does your understanding of it. Perhaps meaning was never something to be found out there, among the galaxies. Perhaps it was always here, in the simple act of noticing, in the gentle realization that to exist, even briefly, within this calm and infinite expanse, is itself enough. So sleep well, fellow traveller in the quiet. You're living in the still centre of a grand, unfolding miracle. The universe's soft exhale,